Minasan, konnichiwa, Zamurai Engineer. In this video, let us learn about another method in numerically solving simultaneous linear equation. We have what we call LU decomposition, okay, or lower upper decomposition. So we have LU decomposition. This is another method to solve a set of simultaneous linear equations. Which is better? The first one that we have talked about, which is the Gaussian elimination, or this one, which is called LU decomposition. To answer this, a closer look at LU decomposition is needed. So LU decomposition meaning we have a matrix that that we want to decompose into two parts. One part is the lower matrix, and the other part is the upper matrix, or the upper triangular matrix. Okay, so LU decomposition method for most non-singular matrix A that one could conduct, naive Gauss elimination, forward elimination steps. One can always write it as a matrix A, which is equal to matrix product of L and U, where L is the lower triangular matrix and U is the upper triangular matrix. Okay. How does LU decomposition work in solving a set of linear equations? We have the following format. The square matrix A multiplied by vector variable X equal to constant vector C. If the square matrix A is equal to the product of square matrix L and U, then we have to substituting the value of A by the L and U, which is equal to A, really. So then after which we multiply by the inverse. So inverse matrix of L. So multiply both sides by inverse matrix. So that is what we call pre-multiply. So we have two types of multiplication because in multiplication of matrix, we will have different products if we pre-multiply and post-multiply. So please review your mathematics in doing this thing, because we have to clearly understand these technical terms, pre-multiply. So pre-multiply inverse of L to both sides of the equation. We are not doing anything wrong. So remember, inverse L and multiply by the matrix is just equal to the identity matrix. Okay, so identity matrix is just equal to 1. Okay, which leads to, okay, so if you multiply these two, so it's just equal to an identity. So we have the following. Now, if identity matrix multiply the upper triangular matrix U is equal to the upper triangular matrix, then of course that is equal, because the identity matrix is a type of matrix that only has elements on its diagonal. It is a matrix with elements on its diagonal, and diagonal elements are all equal to 1. So if you multiply this one to this one, it will just be equal to this one. So just like multiplying 1 times a variable, the answer is the variable. Okay. So in this case, identity matrix multiplied by the upper triangular matrix, that is equal to 1. Okay, and because of this, we simplify the equation to be like this. And now let the matrix product inverse L multiplied by what? The vector constant is equal to Z. So let us just, for what easier, for easy manipulation, this equation, just change the name, which ends with, so we change the name, so we have what? So this one and this one will become this one, okay. So what happened? So negative. So that is our equation 1, okay. And what happened? I can see the other one. Okay, so we have the following two sets of equation. L matrix A times matrix Z is equal to C. Or number 2, and number 2, equation number 2 is upper triangular matrix U times variable vector X is equal to Z. So we have these things, okay. Actually, Z is a vector, okay. It's a vector. Okay. Z is a vector, which is equal to constant vector C. Okay. So let us continue. How can this be used? What is the purpose of this? So given the format of the simultaneous linear equation, which is square matrix A times variable vector X equal to variable constant C. Number 1, decompose square matrix A into 2, which is lower triangular matrix and upper triangular matrix. Then solve the lower triangular matrix multiplied by vector Z is equal to C. We have to solve for Z because vector constant vector is a constant. We can solve for the Z, the value of Z. So Z is a vector which we can solve. Okay, and also number 3, lower or upper triangular matrix times X vector variable is equal to Z. So let us solve this for X. So after solving in step 2 the values for Z, let us use that value as a vector values for the number 3, step 3, and solve for X. And X is our what? It's our target variables to be solved. So we want to solve the values for X. Okay, that is the whole importance of this LU decomposition. Is LU decomposition better than Gaussian elimination? So in solving this equation, for example, matrix A times vector X equal to B, let us define T as clock cycle time and N by N is equal size of the matrix. So let us compare. On your left, forward elimination, back substitution are the process for Gaussian elimination. While on your right side, decomposition to LU, forward substitution, then back substitution are the process for LU decomposition. So there are more steps in LU decomposition than in Gaussian elimination. But let us compare the time clock cycle. How much time will the machine spend, okay, on calculating this? So we have in theory we have this equation for forward elimination and this for back substitution. So we just have to what? Add the time. How much time will be spent in doing this by n by n. So how big is the matrix? N by n. Both of them will solve the same problem. So let us compare. This is very specific. This is very, but let us quantify the time, and comparing the time, you can decide which one is better. So decomposition time clock cycle, and then forward substitution, then backward substitution. So we have to add these three. Take note. Let's add. Please add in your scratch paper. Please add these two, and please add these three. And let us compare. So time taken by methods. So if you add the left side, we have this as total. If you add the right side, we have this total. So we can compare which one is better. So as you can see, they are just equal. They're just equal in terms of time clock, in terms of how long will the machine requires in computing the same thing using different methods. So time clock cycle. So both methods are equally efficient using the machine. Okay. So machine meaning computer. We're going to allow a computer or processor, digital processor, to do this process. Okay, meaning to say there is somebody who will program another program for the two, no, and then compare the result. This is how we compute the time. So if you are interested in computing the time of different digital process or programs, software programs or application programs, these are the formula for forward elimination, backward substitution, and LU decomposition. And there are other routines. This will become a routine in the program. Okay? But to find inverse of A, okay, let us do the inverse thing, because we may need this operation for other purposes. Okay, so time taken by Gaussian elimination, we have this formula, and that is equal to this. So n times this, so just distribute the n, so we have increased degree for n here. Okay, so as compared to the previous one. So time taken by LU decomposition, so just this one and multiply this one by, so this has something to do with the additional operation of doing the inverse. Okay, so this one and this one for forward and backward only. So there is no additional for what, for decomposition process. So after doing this, you will notice we have the following time, and you can immediately compare here which one is better if we are talking about finding out the inverse of the square matrix A, which is what, n by n in size. So this is n to the fourth power. This is n cubed. Okay. This is n squared. So n squared and n cubed. So meaning this is what? Larger. This is larger. So again, this one is n squared. And to be added, this one is 20n, and to be subtracted. So these two terms are lesser than these two terms. So how can we describe this one? So this one and this one, that is multiplied by what? 8, and 32, that is times 4, no? 4. So apparently, if n is 4 or more, no? apparently is if n is 4 or more, so we have LU decomposition as better. Okay, so 4 or more. So if n is 10, so we have what? N is 4 or more. The LU decomposition is better. Okay. What about if n is 10? Already times 3. So 4 is they are about equal to each other. N is equal to 4. But if n is equal to 10, what about n is equal to 100? 25 times better. N is equal to 1,250 times better. N is equal to 10,000, 2,500 times better. So if the computation is more complicated, like what? We can use this in, for example, graphics. Graphics, there are several matrix manipulation because there are so many pixels. Okay, in graphics application and so on. So in purely mathematics things, we can have about some 4, n is equal to 4 is already a good one, or n is equal to 5, but still LU decomposition is better. So for large n, okay, so we can expect that LU decomposition is better. Okay, so that's all for this introduction of the this method. See you on the next video. Again, this is Dr. DrEYPEI, preaching engineering for nation building.